Thanks for everyone to come. Thanks for the organizer. So I'm Yiding Feng. I'm a postdoc researcher at Microsoft Research. And today I'll be happy to talk about this joint work with my amazing co-author, Red from Chicago and Amin from Stanford. Cool, so let me begin our talk. So first I want to show you two slides, so two photos, which you may already see some similar photo quite a bit. So basically this photo suggests that so nowadays we are living in a society where we have lots of data which can be used. And also people argue that there are lots of potential revenue which we can gain from those rich data. And I guess so this situation suggests that we are now living in a paradigm which we will have new algorithmic question, which will how can we revisit the classic problem, but with this new feature that we have lots of data, and it will also provide lots of new challenge. Because of the time constraint, I will not discuss those part in detail. But on a higher level, I think one of the questions I want to ask is that how can we use those data and the prediction power provided by those data to design the algorithm for this new area? And so the motivating example of this project is that nowadays we have lots of applications related to the allocation or assortment for the rental service. For example, like the cloud computing platform like Azure, AWS, or the housing service like Airbnb, or the freelancing market like Samtech. And so if you believe me, so basically for those applications, so it are facing the power and challenge I've mentioned on the previous slides. Cool, so let me first try to introduce the model we consider in this paper. So in this paper, we consider the following online assortment problem. And let me try to describe it to you using the figure on the left. So basically here we have some reusable resources which are given in an offline fashion. And each of the resources will have some capacity. And on the other side, so we have the user which will arrive in an online fashion in a discrete time. And once the user arrives, so the platform will observe a private type, platform will observe a type of this user. And so the definition of the type I will define in the next few slides. After observing this type, the platform can do is to select a subset which will be displayed to this consumer. And we will call this subset assortment. And then so the user, based on her own type, so she will decide which reusable resource or outside option he will consume. And then we move to the second user who also review her type. And let's say suppose that this time, so the platform decides only to display just a single resource to him. And let's say he picked the outside option, and no allocation happened this time. And then we continue to proceed, and so on and so forth. And in the end of the day, so we can reason about how many resources we allocate and how many revenue we collect. And another perspective in this model is that we are considering resources which are reusable. For example, the cloud computing unit, or let's say the house on Airbnb. And specifically, I'm talking about reusable resources using the following animation. So suppose that we are proceeding in time, and once the rental request arrives, so we can decide to allocate a unit of our resource to this request. And we continue to proceed, and there is another rental request. We can allocate another unit. And once this rental duration finishes, so this unit will return to our inventory. Cool. So this is the model, and the remaining thing I need to tell you is about how can we design our user type. So we will try to use the type of user to encode the following information. So the first is that the rental fee this user wants to pay for each possible resource which we can allocate to them. And also, so we'll assume that, so this is a reusable resource, so there will be some rental time generated stochastically from some distribution, which is also associated with this user's distribution. And finally, so we will characterize the purchase decision of this user by the following so-called choice model. Basically, by displaying assortment S, the choice model specifies what will be the probability that element will be so element I will be chosen in this assortment. And there could also be an outside option. And in this talk, we will impose the following two assumptions on the choice model. First, we will assume that we can have an oracle access to solve the optimal offline assortment problem for the choice model we are facing in our problem. And we need to impose this assumption to ensure that the algorithm we provide can be computed in the polynomial time. And the second assumption, which is a more crucial assumption, is that we assume that our choice model satisfies so-called weight substitution property, which basically suggests that suppose I remove an item from an assortment, then it will increase the probability that the consumer will consume other resource. And this is basically the natural definition of the substitution. Cool. So as I mentioned in the beginning of this talk, so nowadays we have lots of data, and which we can use a prediction algorithm to help us to understand the uncertainty about the future. And in this online problem, so one of the questions we need to try to answer is that, so what is the knowledge of the platform about the consumer in the future? So first, we can consider a perfect scenario that they will know the type of the user in the future perfectly. And then another extreme that, so the platform knows nothing about the future consumer type. And the question we want to ask here is, so what will be a realistic information that will be provided about the future type, given that we have this kind of data? And this paper argues that maybe because we have this data and we can use a prediction algorithm, it's reasonable to consider a Bayesian model, where basically for the consumer at every stage, so we assign to a Bayesian type, basically will be a distribution about what will be the type of the user which will be realized from this stage. And in this talk, we will assume that the type are drawn independently across time, and we allow the type distribution to be heterogeneous and will be known by the platform. Cool, so next, let me quickly define, so how can we evaluate the performance of an online algorithm? So we will evaluate the performance by using a standard competitive ratio analysis. Specifically, under the knowledge about this Bayesian type F1 to Ft, what we want to do is to design online, possibly randomized algorithm, which maximizes the total collected rental fee. And the competitive ratio will basically be the ratio which we can consider the worst problem instance, the performance of our algorithm, versus some benchmark. And the benchmark could be any upper bound on the expected revenue of the best online policy. So here, the next question is that, so what benchmark which we want to use? So the first natural one is called optimal offline, which basically knows the entire future sample path, like what will be the user arrive in the future and what will be their choice if we are given some specific assortment, and what will be a rental time. And another benchmark we consider is basically the optimal online problem, which only knows the type distribution. And there are some middle ground regime and some other benchmark which consider in the literature. The first is the cleverent offline, which knows the user sequence, but does not know the exact realization of the user's choice and the rental duration. And in this paper, we consider the so-called ex-ante relaxation, which is a further relaxation on the cleverent offline, which knows the future sequence, but it only needs to satisfy the inventory feasibility in the expectation under the randomness of our problem. And as you can see, so here I list all those benchmarks in a decreasing order as, so optimal offline so will achieve highest revenue, and ex-ante relaxation will be second highest, and so on and so forth. And in this talk, I will show you how we define an online algorithm, which will attain some competitive ratio, which I will discuss in more detail in the next few slides. And it will be respect to this ex-ante relaxation benchmark. And consequently, so it will be preserve the same competitive ratio against the optimal online. And then another thing I want to mention is that our results is kind of the best we can expect, because there will be an unbounded gap between the optimal offline and the ex-ante relaxation. So one reason we want to consider this benchmark, which is the ex-ante relaxation, because it is kind of trackable. Specifically, it can be formulated as a following linear program, which I will not discuss in detail. But this linear program can be solved efficiently by using the ellipsoid algorithm with our oracle for the offline assortment optimization. And this will be an important component of our algorithm. Cool. So here we have introduced our model and how we evaluate the algorithm. So this is the main result. Basically, in this paper, we introduce a near optimal algorithm, which will run in polynomial time. And it will attain a competitive ratio, which will be at least half, and converge to 1 as the number of initial inventory become large. Cool. So in the remaining talk, I will try to discuss the intuition behind our algorithm, as well as the technical difficulty to build it. But to start it, let's start with a very simple intuition. Let's consider an instance where we'll only have a single resource, and this resource is non-reusable. Okay, and here I want to introduce a very simple algorithm which will be near optimal, and I will call it simulation plus discarding. And basically, it will do as follows. So first, it will try to solve the optimal solution from the extended relaxation, the LP we just saw. And then, so it will consider for each user T, once the user arrives, so her type will be realized. And then, so the platform will draw will realize the assortment from this based on this optimal solution. And then, so this way is what we call the simulation part. And because here we only consider a single resource, so this assortment set will either be empty or containing this resource. And then we will consider a discarding phase, which we will remove this item from the assortment with some tiny probability and keep it as it is otherwise. And then we will display this assortment to the consumer. And here I will show you a very simple proof to say that this algorithm achieves the 1 minus epsilon competitive ratio. And the proof is very simple, basically the concentration bound. So first we observe that, so this algorithm, it will satisfy the inventory feasibility. In other words, never run out of the stock, if and only if the summation of the following two random variable is below C, where C is the number of capacity. So the first indicator is that this item is in this sampled assortment as tilde. And the second indicator is that this item is still in the assortment after we do the discarding procedure. And then we can use the standard concentration inequality by observing that in our current setting, because the resources are non-reusable, so those random variables are independent across time. And therefore, by applying the concentration bound you like, for example, the Hofstee inequality, you can show that the inventory constraint will be satisfied with high probability. And we know that if inventory feasibility is satisfied with high probability, because we are generating those assortments based on the optimal solution from the extended relaxation, so it will be a 1 minus epsilon approximation to the extended relaxation. And that's basically finished the proof of that this simple simulation and discarding procedure will guarantee a near optimal performance when we have a single resource and the resource is non-reusable. And when we are considering more general setting where we have multiple resources and the resource is reusable, so there are two challenges we are facing. The first is that because of the resources are reusable, it will introduce the correlation between the allocation across time. And this suggests that we cannot apply the naive concentration argument. And then another more difficult challenge is that because we have this kind of substitution assumption on multiple resources. Specifically, if we discard a resource from our assortment, the consumer will pick other resources with higher probability, and because of this substitution. And this basically will hurt to ensure its point-wise inventory feasibility. And to handle those two challenges, a naive treatment is saying that let's discard our item at a more aggressive fashion. And to do so, basically you need to discard the item with probability epsilon times the logarithm of n and t, where n is the number of items and t is the number of time horizon, which is not that ideal because in the end of the day, we want to have an algorithm whose competitive ratio does not depend on the number of resources and the time horizon. And to do so, in our paper, we use the following two techniques. The first is that we introduce a martingale concentration bound in our analysis to handle the reusability, the correlation induced by reusability, which I will not discuss here. You can check in our paper for more detail. And second is more interesting. So we designed the technical subroutine, which we call the sub-assortment sampling, to handle this issue of substitution as well as reusability, which I will discuss in the next slide. Cool. So this sub-assortment sampling is basically trying to do the following thing. So it will take an input, which will be an arbitrary choice model, and an assortment as hat, and some target probability that we want to ensure that the consumer want to pick the item with certain probability. And the output will be, we will randomly sample an assortment from this subset, and it will match the target probability. And so you can interpret sub-assortment sampling as, so it suggests that if by using this sub-assortment sampling, the platform can cancel the realized choice of the user. In other words, it's equivalent to think that the platform, once he observes the choice of the user, he can cancel it. And because of that, in this paper, we use a sub-assortment sampling to handle this difficulty due to the weight substitutionability and the resource reusability. And cool, so here I will talk about our algorithm idea in a very high level. So it will consider the following 4 steps. The first step is what we observe in our original, the simple algorithm we just observed. We will solve the ex-ante relaxation. And then for each consumer, we will do a simulation. We will sample as assortment. And then for each resource in this assortment, we will try to run some separate procedure discarding, which I will discuss in the next slide. And then we will do a post-processing to invoke the sub-assortment sampling to handle the issue because of the substitution. And here, the discarding procedure, so one you can try to use is a uniform discarding, basically to discard this item with probability epsilon, just as I mentioned for the single resource setting. And so this will guarantee a comparative ratio of 1 minus epsilon, which performs good when the inventory is large. But when there is a tiny inventory, we also provide an alternative to discarding rule based on the dynamic programming, which I will not discuss the detail here. So in practice, so because we have this kind of 2 discarding rule, one of the questions is how can we select the discarding rule for a given instance? And here we provide the so-called, I call the best of both world results, basically tell us how to pick the discarding rule for every resource separately. And we'll observe that from the numerical simulation, so it performed pretty well. So just to summary, so what I talked about today. So today I'm talking about a setting which is a Bayesian online assortment with reusable resource. So some feature in our model is that first we assume that the consumer sequence is unknown, but we know that it's sampled from some distribution. And we are considering a platform can only do the assortment, not by directly to do the matching. And finally, we'll consider the resources which are reusable. And we provide an algorithm which will achieve a near optimal comparative ratio. And they also provide I would say, independent interest of subroutine sub-assortment sampling. And that's all for my talk. Thank you for listening.
Perfect, Amin. All right, thanks a lot. If there are any questions. Yes. And could you repeat the question?
So I saw that the comparative ratio dependency on C is like 1 minus square root of log C of C. So like, do you believe that, so is it tight, or do you believe that similar dynamic programming technique from et is going to give it like 1 minus 1 square root of C?
Yeah, so the question is that, so our comparative ratio, the dependency is at 1 minus square root of log C over C. And the question is that, is this tight? So, so we think this is not tight, especially, we think this is tied up to a logarithm factor, as you mentioned. And when an item is not reusable, we indeed provide a matching bound, which removes this log dependence. I think this will be a super cool question if we can remove this log dependence for the reusable case. And one of the difficulties is that, as you mentioned, so for the non-reusable case, we can use some kind of dynamic programming approach. But for a reusable case, it's hard to use a dynamic programming approach to attain near optimal because one item is reusable. So the state of the allocation is a very high dimensional. You need to keep track. So for each unit of the resource, what its range state. So that makes it become hard to find a polynomial time dynamic programming to handle that issue.
Any questions from the virtual audience? I don't see anything here. All right, thank you. I was told that we have the first speaker.